Okay, well this is a documentation here showing the manufacturing of my latest, trying to make an holographic optical fiber, holographic tipped fiber. The idea here is that we have our hologram is here with the fiber coming down and acting as a reference source for the hologram. And then we have a 100 times microscope objective with a numerical aperture of 1.25 that in oil, that is, so I guess it wouldn't be so much in the air. But anyway, this is acting as a point source for the hologram. And for the object beam of the hologram. This is the setup I'm using for making this hologram. Notice I've got basically the fiber is being launched back here. The actual coil of fiber is about 2 meters long, and then back over here is the beam splitter, and on one side of the beam splitter I have a 0.5 optical density filter, and on this side is a filter with an optical density of, I believe it's 1. And then here's our laser, of course, the YAG laser with the shutter. One interesting thing is that these obviously the optical path lengths are very different between the reference and the object beam. However, the this has a very long coherence length laser of a kilometer, or up to a kilometer. So in theory, this path difference won't have any bearing on or have very little bearing on making of the hologram. We're using a shutter speed as fast as we can manage. I suspect it's probably about a 20th of a second, but I haven't measured it. The setting on the shutter is the setting is obviously not accurate. I think it measures up to 100th of a second, which is the setting we're supposedly using on the shutter, but the shutter seems to be sticking a little bit, and I think it's running more slowly than it's supposed to be. Another interesting feature here is that we need to expand out the light before it goes into the 100 times microscope objective, because you have to fill the aperture of the objective in order to this by putting a microscope objective with this pinhole in front, spatial filter essentially, immediately behind this, the 100 times objective. This is a 10 times objective with a 25 micron pinhole. And the important feature of this, it also cleans up the beam, makes a good beam quality going into the final stage of the microscope objective. I have very good confidence that today's hologram will work. For the moment, what I've done is I've put some Scotch tape, slightly diffuse, on the surface of this glass plate, so that I can see how the two beams are striking the surface of the holograms, so I can get it aligned. Ultimately, of course, I will replace this plate here with a fresh one to make the hologram. Constructing this optical fiber is a very important other thing that I spent a lot of time determining how to do it. And it would be best to actually show how it's disassembled, but I don't think I'm going to do this. Essentially, this you can see this holder very closely. We've got a stainless steel tube running down and getting tight screwed into the. Well, basically there's a stainless steel tube surrounding the fiber, and there's actually two of them. One's serving as a jacket to the other one, and in sort of almost like a telescope arrangement, but it's not actually getting telescoped. The smaller size tube is just the correct diameter to fit over the fiber, the cladded fiber, and that smaller size tube is getting clamped in place by this brass screw here, and it's holding the fiber, the bare fiber that's just been cleaved without any just with the bare ended fiber. And I use super glue, sort of a thickened super glue that has some thickening agent to bind the fiber to the inside of the smaller stainless steel tube. And then this stainless steel tube, smaller one, sticks up above to about this height here at the tip of my finger, and then the larger tube then slides over the top of it to make it to offer better rigidity when it's being mounted here. Just makes it's more rigid than the smaller size tube, and also the bigger size tube is big enough to accommodate the jacketing that goes over the fiber, whereas the smaller size tube cannot accommodate the jacking and jacket, and only the cladding can stay on the fiber, because the fiber itself really has three layers. It has the core, the cladding, and then the cladding is sort of like a rubber almost, and then this jacket, which is probably Teflon. One other thing to note is that I noticed that you have to take off the jacket sometimes in order to expose the fiber, and the real easy way to do that is just to take a razor blade and just gently score the circumference of the jacket, and then just pulling, and it just pulls, it breaks very easily after being scored and exposing the cladded fiber. It took me a while to figure that one out, but it's very easy to do now that I know how to do it. Okay, so what I'm going to do now is I'm going to make this hologram, and Victor's sitting back there working on the computer. We also have a setup here that's kind of interesting. We're just to test out for Victor to work on his software, on the software end of things. We have just a video camera that's mounted, and it's looking at this card that has fringes printed on it, and the fringes are then being passed on to the optical processor, and then Victor can then grab the information off the optical processor and work with it. And here's a television readout of the fringes that the video camera is also picking up. Okay, so we're coming along here. Victor's done a great job with the software and making lots of progress on it. Here's a new hologram that we made that I've already discussed previously on this tape, but it's not new in that sense. It's an old one, but it's made with the green wavelength, and that's what I'm preparing this fiber. Once we've got the fiber built, we can then start looking at this hologram. Okay, I think I'm turning this camera off now, and I'm going to begin making my hologram. Of course, first I have to I have to use this carbide tip and slice up my big plate into a smaller plate to actually mount the hologram. And I think I'm going to use a bit of the sellotape over the end of the glass to go underneath the clamping part of the clamp. That way the metal will be pushing on this sellotape rather than pushing on the glass. And I think I've been having some trouble with the glass getting chipped when I clamp it for long periods of time. And I think putting some sellotape just between the two will help out, and I'm going to try that in this next time. Okay, here's the old, since I'm here, here's the camera that we've built that was also discussed in the last video, but you can see the optics here as we've determined them. It seems to work quite well, although we need to replace this mirror, these two mirrors with better quality front surface mirrors. Yeah. Well, this is me developing the fiber. I have the tip right now in the bleach. I'm just finishing the bleaching of it, and the exposure looks like it could be all right. I'm not sure yet. Of course, I think the object beam is probably a little brighter than it should be. I can see now that after bleaching, the object beam is still quite dark, even though the reference beam is getting bleached out. The object beam still has a little bit of darkness left in it. It's very tricky. This development time is going to be very tricky. I may have to put in a larger density in the object beam. Basically, though, I think the overall development is pretty good, though. The overall exposure time looks about right. It's not overexposed. It might even be underexposed a little bit. So I think we're in pretty good shape for that. And it's just now, so anyway, we'll put this back, after it dries, we'll put it back and test it out. So thank you very much. Portrait shot here. No.
Wow. Okay, very nice.
Well, we put the fiber in, and I'm looking, I can see a point source, I can see my point, but at the moment it's still rather weak, which gives me an indication that it's not quite as bright as I'd like for it to be. Maybe it's not fully dry yet, so hopefully as it continues to dry out, perhaps we'll see an improved brightness. I hope that the brightness will improve. There's a lot of stray light scattering around here, so it's very hard for me to judge what's coming, where different things are coming from. At any rate, we just now increased we had to make a second hologram because these motors are left on, and I forgot about that, so I had to make it again. But this time I increased increased the exposure time by a factor of 2, so now it's probably about 1/10 of a second, and before it was probably about 1/20th of a second. And also I used on the object beam, the optical density filter is now 0.6. I decreased the brightness of the object beam slightly. It was 0.5. Nonetheless, I think there's still, as I'm speaking, I'm beginning to see a little more efficiency coming out of this hologram. The hologram is beginning to work. In fact, very quickly it's beginning to work. I would say, although it seems to have a limited scope so far, it's I think I need to consider this. I'm not quite sure what's happening, but anyway, we are beginning to get some diffraction from it. But till now, the object beam is still very weak in the hologram. Don't know why it has to be so weak. I think maybe we'll give it time and reevaluate it. Okay, you can turn it off now, Victor. Okay, it's a new day here, and yesterday I tried making four different holographic optical elements, and I think, or at least 3 or 4, I think 4, and finally we got one that we were able to begin to get some that worked, and the last one worked the best, but the actual point source is still very weak. We finally decided that perhaps the object beam was actually too weak and the reference beam was too strong, so I attenuated the reference beam by 0.3 rather than with the 0.3 optical density filter and a optical density filter of 1 in front of everything. But we really don't know what it is. We don't know if we have enough or not. But at any rate, I think the problem is that we're not being I'm not really taking this systematic enough. For one thing, I noticed that the mechanical shutter is giving me tremendous variation on the actual exposure times. I tried repeatedly activating the shutter, and each time I could detect with my ears that it was changing its timing, and this is unacceptable. So we actually have ourselves a very nice electronic shutter system, and with this controller box, and I'm going to start using it, so we can very systematically determine the correct exposure time. In addition, I'm going to instigate using a light meter to determine the two beam strengths of the object and reference beam. And finally, this rod here, I believe, could be vibrating even very slightly during the exposure, and of course that's going to destroy any diffraction efficiency. So I'm going to try to develop a way of bracing the underside of this at the precise position that we want the plate, this tip, to be located at, bracing it with a little post coming up from this point. In some fashion, we need to brace it so that this has no possibility to vibrate. Given these new factors, I think we might be able to improve our efficiency considerably. I was going to try to see if you could actually see the point source with the camera, but so far I'm not succeeding in getting it to focus properly. You still really can't see the point source. You can only see the reference beam and where it hits the plate. The point source is located in the middle of this beam. No, it doesn't seem to be working. Even here you can't really see it. It's not really... Unfortunately, it's not possible to see it with this camera. But there is a point source of light located within the hologram. The process now is a matter of making as many holograms as necessary to determine the appropriate exposure time to maximize their diffraction efficiency. And we'll just have to do this systematically rather than doing it haphazardly like I have been. Okay, that's all for now. I'll talk more about this later. Okay, well, it's Saturday, and I finally succeeded in doing what we've been trying to do for about the last God knows how many months. I've managed to make today a holographic optical element mounted on the end of a fiber, which succeeds in, at least demonstrates the feasibility of this system, of this the possibility of this to work. Basically, I was able to get a good hologram just now and I'll discuss briefly what I did, I think, to improve the quality of the hologram. This hologram, by the way, is quite bright. I don't know if I'm going to be able to pick it up with this lens effectively, but this is very bright, and but it doesn't really want to focus on it for some reason. Okay, finally, what did I do? Well, I put in an electronic shutter. Here's the universal shutter system using a 2 millisecond exposure. I've got an electronic shutter now in the back, replacing the mechanical one that's behind this card. There's an electronic one there now. And also what I did was I took out because of the faster shutter time, I was able to remove all the optical neutral density filters. I no longer use neutral density filters. I just expose it to the faster shutter speed, which is about 500th of a second, and that was sufficient to give me a low. I was able to get a good exposure without, just on the first try. I was able to. It looked like it developed pretty nicely and not too quickly. I'd say the diffraction efficiency is, it's hard to judge. It's probably about 10%, but still, it's a step in the right direction, and we might need to I think I could probably optimize the exposure time even better. Another thing I did was I mounted this mechanical stop here that the wire, the probe comes up and rests against. Hear that click? That click is the probe resting against the mechanical stop, and that provides a damper, so there's absolutely no, very little vibration should actually, there should be very few vibrations in this thing. Essentially, it should be completely damped. Another thing I did is I mounted this collar here to the right of the probe as a way of providing a accurate lateral position for the probe, so we can get the lateral position right on the probe and not have to worry about that. What else? Another thing I did was I took away the sellotape here on the end of the glass. I put sellotape in there earlier thinking that it would help prevent it from shattering the glass, but what I've learned is the sellotape doesn't, what happens is it doesn't, the glass doesn't stay firmly mounted, and it ends up twisting around in its mount, and so it's no longer an accurate position. It's not, the hologram is no longer accurately positioned to the fiber. So that was another critical thing. Another thing I did was I remounted the tip of the fiber so that this screw, there's actually 2 diameters of shaft here on this tip, and the screw is still firmly clamping. It's still being clamped against the smaller shaft diameter. However, now I have the larger shaft diameter actually protruding into the hole, into this hole here of this larger piece of metal, so that the big shaft goes up, just missing the screw, and then the screw screws into the little shaft, and that way they both get bound together. The tip, because of this, the actual tip is actually moved a little closer than it was previously. Sticking out, the shaft is sticking out a little bit on the other side, and that's putting this a little closer to the glass. I don't know if that's good or bad. It does make the spot size on this glass plate smaller than it would have been, and the F number of the glass, the hologram, is determined by the spot size and the distance that the spot is away from the microscope objective. What other comments? One is, originally I wanted the slope of this here to be about 45 degrees, so the glass plate was more or less mounted in a vertical position when it's being in use. However, the microscope objective prevents me from doing this because the objective itself has a slope that is not 45 degrees. It's probably shallower than 45, so I can't make, this has to be more shallow also. It has to be more steep, well, more vertical. It has to be more vertical than 45 degrees in order to match the slope of the tip of the microscope objective. Otherwise, you end up getting a shadow projected across the reference beam by the end of the microscope objective. And so we match the slope of the microscope objective to be equal to the slope of this probe in order to optimize the distance that this microscope objective can be mounted away from the glass slide. I might even investigate. I still want to investigate trying to get the tip of the microscope objective closer to the glass slide in any way that I can to expand the F number. But I think the F number right now is sufficient. The numerical aperture of my hologram is sufficient for us to do our experiments. I could live with the numerical aperture just like it is. I would like to try to expand it slightly, perhaps. It might be better just to make it a little bit bigger, but I think we can live with it as it is. I want to try to increase the diffraction efficiency if possible, maybe by playing more with exposure times. But the hologram is oh my god, it's probably about 100 times brighter, or maybe 1,000 times brighter than the original hologram that I made a day ago. This one is definitely diffracting very well in the way it's supposed to, and I'm quite happy about that. Okay, so that's an update of this project, and we will continue from here. Okay, well, today is Tuesday, and we are, I have spent the last week, working more on the fiber and also rebuilding this camera system that you see before you here. What I have done is, let me put in a top view of the system. This is showing the overall view from above. Basically, we have over here is where the laser ordinarily sits in this platform, and the shutter sits in this square. Then we have a beam splitter, and now the reference beam for creating the holographic optical element goes through from this side of the table and progresses through to this collimating lens, and then we have these two mirrors here who these two mirrors then direct the light through into this holographic optical element and across to the other, so that it reflects off these two mirrors, and the alignment is made so that the reflection then progresses back through this pinhole and through this microscope objective, so that we know that the two sides of the system are in alignment with each other. As you can see here, there are actually, for making the hologram, we have, for making this hologram, we send the light in from this direction, using two different angles now for recording into this hologram. This is the same arrangement that I showed previously, except now I've replaced the big mirrors that were located here with small mirrors, simply by reversing the direction that the light reflected off those mirrors, and by having the light come from this side instead of coming from this side, I can use small mirrors instead of having to use large mirrors to accomplish the job, and this is much better. Now the beam splitter then sends the light over to this mirror, which then reflects off. It's a bit hard to see here, but this mirror then reflects off of the lower mirror, which then reflects off another mirror mounted. I'm sorry, it first hits this mirror above, then it goes down to this lower mirror, which then reflects up to this mirror. So it goes into this mirror, down to the lower mirror, across to the higher mirror, and then out the spatial filter microscope objective arrangement, which then forms our object beam, which then progresses through the holographic plate, through the lens hole, the two big lenses, and into the hologram over here. And today I've also mounted the removable, I'm just showing here the removable platform that is going to be used with the pulse laser work, where the pulse laser, for the pulse laser, these two mirrors here are removed, and instead we use these two mirrors to direct the light through the hologram. And we have some optics will be placed in here for creating two collimated beams, but reference beams, but these optics are not finished yet, so I don't have them installed yet. But then here is the input mirror. These two mirror holders take the two incoming beams from the laser and then direct them to be collimated and reflecting off of these two mirror mounts, and then through this hologram to reconstruct our reference beam back through these lenses and into this hologram, through this hologram. And that's the basic arrangement that we have. And I think it's too big of a setup to show you the entire all the optics in one go almost. If I put it on its side, I might be able to get most of it, but even then, it's too much to get all of the optics into the showing all the optics put together. You can just about do it here, and then our laser sitting here. Okay, so this is virtually finished for working, for making, well, we can use this now to make continuous wave holograms immediately by putting the laser on where this is. When we go to do the pulse work, there will be another component added. There will be a positive cylindrical lens mounted directly in front of the hologram here, and a surrogate glass pipe or glass window placed here, curved glass window, for taking into account the aberrations of the engine optics, of the engine cylinder wall. And that will sit right here. And that's it. That's all we need for doing the pulse work in the engine. Now, going back here, I'll just want to recap on some of the latest attempts I made with this system. The very last thing I tried to do was to make an edge-lit hologram, which unfortunately I never, I didn't succeed in getting it to work. But I think I have a pretty good understanding as to why it doesn't work. But I thought I would just briefly show what the final system setup was that I used in making the edge-lit hologram. I think I got the exposures about right. Basically, I'm using a holder that looks like this, and it's resting at an angle to the microscope objective. As you can see, it's hitting at an angle, and the light is actually getting sent through the edge of the holder, like this. You can see here's the holder, and the fiber, the light comes through the fiber, launches into the edge of the glass. It was very successful in terms of the holder works extremely well. It holds the glass very nicely using two screws and a slot, and then a screw here to hold the fiber. I'll maybe set this down here so you can get an idea about how it looks. And this is what it looks like on this end. Unfortunately, the reason this system doesn't work is, as far as I can see, due to the fact that here the angle is just too shallow for the beam getting launched into the glass, and there's not enough light getting into the emulsion. Most of it is getting critically reflected at the emulsion glass interface inside the glass, so it doesn't get into the emulsion very well. Also, the polarization is a problem. We have to make sure that the polarization is such that that the light interferes with the object, with the microscope beam. The other thing is, this is single mode fiber, and it's not polarization preserving. And what I found is that the light actually becomes circularly polarized and doesn't have much linear polarization to it. It's not linearly polarized at all. It's very depolarized, and so that a lot of the light is getting wasted and not being used for the actual interference process. This is not the case with the other fiber that I developed, which is sort of sitting down here. I'm going to put this one fiber away in a minute. First of all, let me just say that my exposure time for the edge-lit hologram is 40 milliseconds. 40 milliseconds, that's quite long. When I made the other fiber, I have made another fiber that does work very well. And I will be showing you this more shortly. At the moment, I'm going to have to clean this up a little bit before I talk further. Okay, let me just add about the design of this. If we were to make an edge-lit hologram that did function, what we would need to do is introduce about a 10-degree angle, have the fiber be launched into the edge of the hologram at an angle of about 10 degrees with respect to the surface of the hologram. And this 10-degree angle would be enough for the light to penetrate, to not critically reflect, and in fact to enter into the emulsion and interact with the emulsion. But right now the angle is more about somewhere around 5 degrees or less due to the natural divergence of the fiber, and this angle is just not enough to get good edge-lit properties. This is the successful hologram, the one that we've successfully been able to make into a probe, and hopefully it'll focus here. As you can see, this is an off-axis hologram. The reference beam is introduced from the outside of the plate, and the object beam then going through the plate like a transmission hologram. When we actually make the hologram, we have our 100 times microscope objective down here, and this hologram then comes down and rests against this metal post. It's identical to my discussion that I had about a week ago. This is very similar hologram, but this is a newer one that I made since the last videotaping a week ago, and this hologram is the best one I've made so far in terms of its diffraction efficiency. We're using a 2 millisecond exposure on the hologram, and the beam, there is no attenuation in either the object or the reference beam. And this is using a single mode fiber, but this fiber is a polarization preserving fiber, so this fiber does not have, this does preserve the polarization in the reference beam very well, and that seems to be more important than I thought it would be. It's quite important actually that if you don't use a polarization maintaining fiber, then your fiber will not be polarized. The light will not be polarized in the fiber when you are finished. It's quite essential to use polarization preserving fiber. I did not recognize this until I just started experimenting for the first time ever, with non-polarization preserving fiber. Here's our beam launcher here into our coil of 2 meter long fiber. And if we look at the beam, it's fairly bright, and you can't really see it because it's not really capable of, the lens isn't capable of picking up the intensity. It's too intense. So this is our final product that seems to be working the best. I think I will go ahead and try making another one of these holograms, only because this particular hologram has some scratches on it, and so the scattered light has some fairly large scratch features in the far field from the hologram, and I'd like to try to clean up the beam as much as I can, and so we'll try to make another one, but basically we'll keep the same parameters. Another improvement I made with this hologram from the previous ones shown more than a week ago, is that I mixed up new developer, and the old developer was getting quite old and black, and it was I think it was really past its use time use by time really. And after mixing up the new developer, I think these new holograms have a much better diffraction efficiency, partly because of the new developer, and also partly because of getting this new shutter that allows us to have very accurate control over the shutter times and very fast shutter times, so we don't need to use any attenuation plates for making this kind of hologram. We're quite happy to use the existing the light in its full form. Okay, I just want to point out again the features of this system. We have a 100 times microscope objective there. Followed immediately behind it is a 10 times beam expander with a pen holder, clean up the light. Back here, we've got a turning mirror. Down here, we have our beam splitter, and then another turning mirror and our shutter, electronic shutter, and the laser. And of course, down here on this side is the fiber optic launcher. And that's all there is to it. These optical paths are not matched at all. In fact, with the 2-meter fiber, the path length difference is quite great, probably in excess of 3 meters between the two beams. But this is not a problem because we are using a laser that has kilometers worth of coherence length. This same issue applies back here on this original setup, where we have, again, quite a long difference in path length between the object and reference beams when making that holographic optical element back there. This the path length here is probably also 1 or 2 meters of disparity between the two paths. But then again, using this new laser with such good coherence, it's not like a helium neon laser where you have to match your paths within a few centimeters. This system does not require that, and it makes it more flexible for us to test out, to introduce novel geometries. Okay, and there's Victor sitting in the far corner of the room there working on the computer, and he's coming along very well with the programming. Every time I turn around, he has made improvements to the system, to the software side of the system. Okay, so that is all, and I will be probably making another hologram here, and then I will switch to. I'll have to take these components away so that I can put back the original video camera with the hologram, and then mounting this holographic optical element in front of the hologram and the video camera so we can start using it for analysis of holograms. And that's really what this is built for. It's unfortunate that I have to take these parts away, because then because in the future when I need to make a new hologram, I'll have to put them back. And I guess that's not a big deal. It's just that I worry a little bit that I'm able to get it exactly back the way I made it this time. I will take down measurements of the key positions of these slides so that we can at least put the slides back into their original positions, hopefully fairly quickly. Okay. On that note, I will be putting those measurements into the lab book, I believe, instead of doing it on the videotape here, since it's sort of hard to get to with the videotape. Okay. In the last night, I tried to rebuild this holographic optical element. In fact, I built it several times, but I have yet to be completely content with the diffraction efficiency that I'm getting in the hologram, and I've been thinking about some of the problems that I've been having controlling the experiment adequately. I think it's quality control that's giving me, it's not quality control, but lack of parameter resolution that's giving me some trouble. For instance, here on the exposure time, I'm using a 3 millisecond exposure for the last hologram, but the only other setting I have is 2 milliseconds or 4 milliseconds, but the difference between 2, 3, and 4 is a huge amount of energy. It's on the order of, well, that's about 30%. What is it? I guess it's between 2 and 3 is something like 30% change in energy of exposure, and that's not very much. That's not very satisfactory when it comes to trying to get the right exposure time. The reason for this is because my light levels are so high coming from the laser that I need to use these very short exposure times unless I attenuate the light first. And I believe today that's what I'm going to have to do. Also, so what I'm probably going to do today is add a density filter of 1 behind the beam splitter so that I can then change it from 3 milliseconds up to 30 milliseconds. And that 30 milliseconds will then allow me to have much finer adjustment in the parameter settings. Now, something else I did yesterday was I changed the fiber optic mount here, and I moved the fiber further away from the hologram because I wanted to try to get it to illuminate a bigger area on the hologram. When I did this, the quality of the fiber, I had to refinish the end of the tip of the fiber because the tip got damaged, and my new fiber has a slight reduction in the beam quality from the original fiber, from being perfect. It's only slight. I think we can live with it, but it's otherwise I'll have to rebuild the whole tip in order to, if I want to improve it any further now. But I did move the beam back further, and this should allow me to get a bigger area on the hologram, and that would maybe give us a wider field of view for the point source. Because of this, the reference beam intensity is less than it used to be, and so I've introduced an attenuator in the object beam here of 0.3 in order to reduce the object beam slightly to compensate for the weakened reference beam. So that's the story we have right now. I've been paying a lot of attention when I make these holograms to try to get the surface quality of the glass and of the emulsion very clean before it dries. I try to remove any particles that I see that are sedimentary particles from the chemicals by gently rubbing the hologram under a stream of water, and then during the drying process I try to shake off all the water droplets from the area of the active hologram before it dries. But I try not to touch the hologram at all after washing, because I don't want any of my fingerprints or any contaminants from any cloth sticking to the holographic emulsion and creating aberrations that end up hurting our overall view light pattern, or far field light pattern. Today, I think I'm going to do a series more of holograms to try to learn what the best optimal exposure time is, and also I might experiment with moving the point source a little bit even closer, slightly closer to the hologram. I'm not sure though. I think I'll start by leaving it as it is, the actual distance of the source. One thing that I also noticed just now is that the point source is about a half a millimeter too far to the right, maybe 1 millimeter too far to the right, right of the reference beam center, and so I may have to try to readjust that. I may readjust that next, try to compensate that position slightly to make it a little more centered. It's pretty well centered though, in general. I guess the other thing is the brightest part of the hologram. When I look at the hologram that way, it is considerably lower than the center of the hologram, but if I there are some issues there too. The vertical position of the point is lower than it probably is lower than the center as I view it through its brightest position. I think it's acceptable. I think I think we'll leave the vertical position the way it is. Another thing is there's some stray light reflecting off the sides of the microscope, insides of the microscope objective, because the incoming illumination to the microscope objective is larger than the walls of the barrel. So I think I'm going to try to put an iris in behind the microscope objective to stop that stray light from getting through in the future. We'll try that one also. Hopefully that'll improve some of the quality slightly. I think the exposure time is the biggest thing. Second issue is the object to reference beam ratio. I don't have a light meter. We need a light meter ideally so we can quantitatively record the brightness of these holograms as we're making them, and trying to determine what the optimal get an optimal object to reference beam ratio through using a light meter, and then finding the best diffraction efficiency by using varying the exposure times and finding the optimal exposure time. And putting okay, that's all for now. I'll talk more about this in a little while. This is off the subject completely of holography, but this is something I call a grass house, or maybe I should call it a pod. This is a scale model, and this is completely unrelated to what we're doing here, but this is something I've been working on at home that I'm quite interested in, and I just want to get this recorded on video for posterity. Okay, this is Monday, and this is showing the system as it now sits with the new wand, which we've now has been dubbed holographic wand, in front of the hologram, and you can see the basic arrangement here: the video camera, holographic wand, and hologram. And at the moment, we need to. This wand is producing bright enough light, but at a divergence that's not not high enough for all of my needs. And so I will be working on increasing the divergence of the wand, and the lens on the camera here needs to be rebuilt with a lens of the correct focal length for our project. At the moment, this lens is just a lens off the shelf, and I don't even know the focal length of it but it's not the right kind of lens. It's an infinite conjugate lens, and well, we need to rebuild this with a well-defined known lens of a focal length that matches the aspect ratio of our new system. And that pretty well summarizes the situation right now. The wand is working, but it's not quite, doesn't have the divergence I want. Another problem is that this hologram here is working, but it doesn't have the fringe spacing that I want. The initial bias of the fringes has too few fringes across the hologram. I want to have a larger number of fringes so we can get the push the correlation spot further away from the DC point. Okay, this is the hologram running. As it's running, you can see the the wand is working with its bright light point source of light, and the fringes are shining into the hologram and forming onto that camera over there. On the screen back here, we can see the fringes that the computer ends up seeing, and so these fringes are very well defined, but they are in fact too few. There's too few of them for our needs right now. In fact, right now there's about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 25, 26, 27, 28. There's 28 fringes across this screen right now. And ideally, we want to have something on the order of something to the order of let me block this laser beam. Okay, here is probably the more of the ideal. I've basically we've just put in this card here, which has fringes painted on it, and this is the fringes that we see from this card. You can see the spacing is much finer. In fact, it's about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 30. This has 57 fringes going across the diagonal, as opposed to the other one, which was 27 or 28. So the other thing to bear in mind is that this lens is not viewing. This lens here does not see the full scale of from top to bottom of the fringes. In fact, the starting point of the lens is right here, and the upper limit of the lens is right about here, which is not bad, but from here to here, that's actually not too bad, but we would like to have it extend all the way down, and then from the right scale is here, so the left scale would then be about here, going from here to here, from here to here. Okay, well, actually this lens is focusing on approximately in the right area of what we want, but nevertheless, so this hologram needs to be rebuilt with with higher fringes, a higher bias of fringes in it. So we will work on this next. Also, we will work on rebuilding this lens here as well. Okay, so I think that pretty well summarizes things right now. We're going to leave this wand in place, even though it's not perfect, but it's pretty close to what to being ideal. We are going to we'll leave the wand in place, and we will we'll start by improving this lens if we can, and also improving this this hologram. We're going to rebuild this camera system here, so that actually this hologram here introduces a higher fringe shift into this hologram via here, by moving this pinhole a greater distance. Now what I have to do is go back in my video notes and figure out what pinhole distance I did move, what I moved the pinhole at to get the fringes that I calculated, and probably double that amount. If I remember right, I think it was 100 microns, but I'll have to check on that. just to point out that I did write down in my notes here some of the details about the holographic clamp. Then I did a bunch of tests making different holograms for making the wand, the holographic wand, and I tried measuring accurately the brightness of each hologram with a meter, with a light meter, and testing different exposure times. Here's the light meter that I've been using. Really meant for helium neon lasers, but it seems to work fine also for the green. And it gives me a relative brightness that I can check against. So I did lots of tests, and all this is recorded in the book, which I'm not actually trying to put all onto video here, but this is in fact the notes of the book. And so finally, the final thing I did was I wrote down the actual positioning of all the optics when I made the for making the holographic wand, so that I can go back and reproduce the positions of everything. This shows the final setup for including the optical density filters 0.3 and 0.5 in front and behind the beam splitter that I used to make the very last hologram. I used a 1 millisecond exposure, and I got a brightness value of 27, which was the highest that I've obtained so far. However, there's a great deal of surface imperfections on the last one, not because of scratches, but more because the emulsion seems to have wrinkles in it, and so the light is somewhat dirty. The other problem is that the center the center of the reference beam is much brighter than the edges, and the consequence of this is that the the angles of divergence is less than originally desired in this new hologram. So eventually I'll rebuild this, but not. But for now I keep it, and we move on to solving other aspects, other problems that we've already discussed with the system. Breakthrough, changing the size of the window. He's been able to get some things working. He can now make the window size of the frame grabber very much smaller, and dynamically shift it around to follow the peak of the spot. So, can you actually see the correlation spot on this?
It's too near. This is the one that I used cardboard.
Okay.
That's the peak.
It's too near the center, isn't it?
Too near.
Yeah, so we'll have to. I counted it. This has 27 fringes in it, and the one that you've been using has 57 fringes to get it pushed away from the peak. So we'll fix that. We'll put in I'll make a new hologram with more fringes in it. A small number of fringes here, as you can see. This is the small number of fringes. With the lights off, they look quite good. And here's the correlation. Okay, and this is showing Victor's program with the correlation spot in the corner, and then showing the deviation of the X and Y position. Showing the correlation spot right here. Okay, this is the system as it is. This is still the same day as what I talked a few minutes ago, but just showing that this is the new lens holder, the new surrogate cylinder wall holder, although it's not glued down at the moment. It's mounted here on a gimbal system to allow for tilt, and the magnetic base at the bottom allows us to slide it around to give XY positioning. Here are the new lenses that Vic made up, lens mounts, for holding the lenses for the pulse laser work, and they're looking quite nice. Just showing that. Okay. I'm not doing anything with this camera at the moment, although I will rebuild this holographic optical element very soon to give us better fringes, more fringes in the hologram. Initially I won't work with the surrogate cylinder though, I'll leave that out for the initial work. Then back over here we have a newer system also. This plate holder has been replaced with a lower one. So this is now, and this is the surrogate piston mount here to go inside of this system. Right at the moment, I don't have the surrogate wall here, but this will fit in just like this. And now this camera is mounted on its side. It's just resting on this platform here, but this camera now has the aspect ratio reversed 90 degrees, flip 90 degrees, so that it because then ultimately it's this height here is going to be the long dimension, the short dimension is going to be across here. With the new cylinder, engine cylinder, it's going to have this change in it. Here is the correlation function. Not very good right now, but there it is. And then here's the fringes seen by this system. Again, it's not perfect at the moment, but it's quite good. Hello, I'm up in my office now, and basically I found the computer program that I wrote in Mathematica a few weeks ago, called Particle Shift. And in this program I calculate the fringe spacing that the hologram should have for a given pinhole offset. And for example, with a pinhole offset of 70 microns, then I have plotted a graph down here showing the fringes in the hologram and what it should look like. Now the problem is, right now I don't know the exact dimensions of our viewing space, and but I think with a reduced field of view, the results are very similar to what we're seeing downstairs. What I have to do now is go downstairs and check to find out what the actual dimensions of our viewing area is, so that I can compare the two with each other, and then I'll know more. I'll be able to come back up here and then redo these calculations, and then determine what the best image shift should be. As a reminder, okay, so this program indicates that the last hologram we made, we used 70 microns as the particle, or as the pinhole shift, and the downstairs I measured 27 fringes across the screen, which is pretty well consistent with what I'm getting here. Although this area is not quite, this area produces 37 fringes, but I think this area is larger than the area that we are using downstairs. So I have to go back downstairs and check on it. Ideally what we want is about 57 fringes. 50 fringes to 57 fringes would be ideal for our application. And I will leave it at that for the time being, and from there we can determine what the optimal particle shift should be after we've figured out what the size of our hologram window actually is. I'll get back to you in a bit. I've used the ruler and I've measured the geometry to be 9.6 millimeters vertically and 5.7 millimeters horizontally. That is the result of this camera being mounted where it is on its side, so that the vertical geometry is taller than the horizontal geometry. Let me check on the distance that the pinhole is, that the camera is from the plate, but I believe it's fairly accurate to what we want. Okay, yes, this camera pinhole is located about 425 millimeters away from the hologram, which is what I designed it for, 425 millimeter distance. Okay, now we'll go upstairs shortly and do some more calculation. Okay, I reprogrammed it with a new width and height, with the measured width and height of the camera down below, and I get a total of about approximately 32 fringes in our field of view for the camera. Now, I guess this is reasonably accurate to what we'll have in the long run. So for the time being, now I'm going to try to determine the appropriate spacing, the new spacing that we need to get about 57, 58 fringes across this field of view, the same field of view, and that's what I'm going to do next. This field of view is with 70 micron shift, the old image shift. Okay, so I have found that with 125 micron shift, I'm able to get 58 fringes across our field of view, and that corresponds very nicely with the fringes we are using presently with the optics system on the printed cardboard, which works very well for Victor at the moment. So I have every reason to believe that this will work. This value will work well. Will work also very well for Victor. So I think my next step in this process is to rebuild the holograms in the camera to give me this 125 micron image shift, and take it from there. At least that is one of the major things that I will do next, and then I can well, we'll discuss it then. So that's it. 125 microns is the magic number, and that allows us to get our shift that we want. Okay, I've got the optics set up now to make this holographic optical element here. It's located right here. What I've done, I don't know. I've got all the optics aligned and on the camera, and I've installed this electronic shutter back on the laser here, back here, so that I've got electronic shuttering of the light. I've used this light meter here, this helium neon light meter, to measure the brightness, relative brightness between the object and the reference beams, and I've discovered that the object beam is quite a lot weaker in brightness than the reference beam. So to compensate for that, I have put in a 0.6 neutral density filter in the reference beam path. That corresponds to, after doing that, my reading is still a 2-to-1 beam ratio, so the reference beam is still twice as bright as the object beam. And so I think that'll, of course, if you have a 1-to-1 beam ratio, then the modulation is 1, and of course you get the highest modulation, but you can run into trouble with having exact beam ratios. So I think I prefer to stay with a 2-to-1 beam ratio. And we're more or less ready to go now. I've got the optics aligned so the light propagates through this pinhole when it comes through this system, and then when I put the laser here, then the light now bounces through this system and goes through this pinhole there, so that it traverses both directions, at least pretty close to perfect. Here we've got our pinhole here. This is a 5 micron pinhole, and I believe this is a 40 times microscope objective. And we have a polarizer here, which will make the light only pass the vertically polarized light through the system, and that is pretty dirty. This is a pretty dirty polarizer, so it is contributing a little bit of dirt and a little bit of noise to the overall signal, but I think it's acceptable like it is. And what else? I have yet to determine the exact exposure time that I'm going to use. I think the exposure time will be on the order of a tenth of a second, perhaps, at least to start the ball rolling, to get an idea. I have to make a judgment about that, but I think anywhere from a half a second to a tenth of a second I will use for exposure. I think perhaps more on the order of a tenth of a second. Okay, and of course we'll make two exposures here by picking this mirror out of the way and using the second reference beam. And when I do this, then I shift this pinhole 125 microns along this diagonal axis, and that will allow me to have get an object shift, put in an artificial image shift. And then after I've made this hologram and I'm satisfied with it, then we will move on to making another hologram here with the new fringes, and hopefully these fringes will be higher frequency and will allow Victor to work with that hologram in the future. Things are looking very nice. I think we're in good shape, and now I'm ready to push on and make these holograms, and then I'll tune back in here. A hologram of this HOE. I made this new holographic optical element here, and what I actually ended up doing was switching the filter to be a 0.4 optical density here, even though the light meter indicates a 0.6 is the right one to use for 2-to-1 modulation. With my eyeball, it looks to me like that it was too weak. But at any rate, I think maybe the 0.6 would also work fine. And at the moment, I'm just going to leave it at 0.4 for doing some initial studies here with making a hologram here. At any rate, we used a 0.4 optical density filter with a 20 millisecond exposure for each exposure and a 125 micron shift on our pinhole. And the pinhole distance is 425 millimeters away from the plate. I did forget to put in a new holographic plate, so this is one that's got dust on it and maybe a few scratches, but it wasn't too bad. I think the plate is it does seem to have some scratches, so I think if I'd make it again, I'm going to put a new plate in here. But this is the other thing was I had to put some baffles in to block some of the light. And what I did was actually I put a pinhole oversized iris here, and that blocked the light escaping around the spatial filter going into this lens. And then I had to put a second piece of cardboard underneath it, and that blocked any light coming through from the bottom, because I was finding that there was a fair amount of light escaping into the system, into these optics here from around that area. The other thing I had to do is I had to put a cardboard right up here in order to block the light escaping from the laser going straight into this hologram. And furthermore, I put this card right here so that it would block, so that the reference beams would be deflected away from these optics here, so it wouldn't get channeled back into this hologram by accident. So that's what I did, and we will now try making a simple hologram with this particle tank located right here. We're going to make a simple hologram using a good plate here, and so we can then test to see how well it works with the new fringes. And I'm going to do that straight away so that we can get that loaded in for the optical processing unit. Okay, I just made 4 holograms with the big holograms that is right here of a stationary object, using the 2 reference beams. And the first hologram I exposed for 25 seconds for each exposure. The second hologram was for 10 seconds for each exposure. The third one was for 5 seconds for each exposure. And the fourth one was for 2 seconds for each exposure. Apparently, at least from my observations of how quickly things turn dark and develop, the 5-second exposure seemed to be fully developed without being overly developed, and the 2-second exposure looked like it was slightly underexposed. So I would vote for the 5-second exposure to be used for future holography, but that first I have to check the diffraction efficiency to see if that works. Come in. Hello.
Don.
I'm my videotape. This is my videotape chronicle. Yes, but I've just finished it, so for the time. Okay, so we are. I've completed making the 4 holograms last night, and the 5 to my basically what I expected. We got what I expected more or less. The 5-second exposure works quite well. Also, the 2-second exposure works extremely well. In fact, that's what I'm using right now is a 2-second exposure in the in this particular hologram. This hologram is mounted with a 2-second exposure. As you can see, the fiber optic wand is positioned here, and the hologram is there. And the wand is now in the particle space, and the fringes are getting projected back into this camera and on the screen you can see these fringes. They're just what we were hoping for. I haven't actually counted them. Maybe I'll do it right now, turning off the camera first, but I expect them to be over 50 fringes. Let me just do this right now. I'm turning off the camera for the moment. Yes, it's exactly 56 fringes from one end of the diagonal to the other on the screen, which is exactly what I calculated it should be, which is all very nice. And the fringes are quite bright and very easily discernible. The wand is doing a good job, and everything is working very well. Unfortunately, at the moment, the correlation space is out of focus. This is because Victor's computer is turned off, and I have to make a confession that I don't know how to use his program, don't know how to start it up. So I must wait for Victor to come back later, and before I can show the correlation space. But that's basically it for now. Using 125 millimeter, or micron rather, 125 micron displacement of the particle image shift. And that has given us the 56 lines that we were hoping to find. Even though this is out of focus, you can see it is distanced quite nicely away from the DC spot, and that should allow us to easily get the information back that we need. The wand is working well, although it still needs to be rebuilt with a wider spread of field with a wider numerical aperture here, because it's not reaching side to side as much as it should. But for one position, for one point in space, it does reach the entire field of view, as you can see, and that's quite nice.
Back to this afternoon's session. First speaker is from Loughborough University, Dr. Barnhurt. I'll just hand over to you.
Okay. Hello. Perhaps many of you saw the demonstration in our lab an hour ago or so. I'm basically going to be discussing why I'm here in England with a person with an American accent at Loughborough University, and some of the exciting things that we were doing here. Originally, I began my career at the University of Illinois working with Professor Ron Adrian, and at the time, that's well over 5 years, well, it's about 7 years ago now, when I began work there. We developed a holographic, the world's first holographic PIV system for measuring, taking holographic measurements in a fluid environment. And what I'll begin today is briefly discussing what I did at the University of Illinois, just to give you an overview of the direction we're headed for here, and then discuss what we are doing that's different from the University of Illinois. Hopefully all of you are pretty well aware of what particle image velocimetry is and the basic ideas behind it. What we are doing is extending this into the third dimension and using a hologram as a recording medium instead of a two-dimensional camera or planar camera. And originally, we did this completely digitally. We have digital analysis at the University of Illinois to analyze the holograms. And today we are trying to do as much as possible optically, not just because it's a nice idea, but really because it's a better approach. Maybe I should back up to explain why do holographic PIV at all. What we are able to do is take simultaneous measurements in millions of places, millions of locations within a volume in one instant of one time interval, and then measure the three-dimensional velocity field of that volume. And this is very important for computational people who are doing computational fluid mechanics, because they set up initial boundary conditions that they don't necessarily know correlate with reality, and there's no good way to set up their computations when we can't measure the boundaries in reality. But this system allows us to actually measure all the boundary conditions at one instant in time, and it is in a sense, frozen in time approach. We're only looking at one instant in time, but we get all the information, the spatial information, at that one instant in time. In particular, we are working with Rover and working with their glass engine project to study the combustion and the combustion cycle inside of a working combustion engine that has a glass cylinder, which many of you probably saw also at the tour recently, just now in fact. Okay, because this is an unusually long session, normally we are given about 10 minutes to give a talk, but I actually have a half hour to talk. So I'm not going to be too worried about talking fast. And if you have any questions, I don't mind if you want to interrupt me during my talk, okay? Otherwise, if you want me to tell me to hurry up, I can do that also. Well, to begin with, these are actually a collection of overheads. I have to confess, I didn't make for this talk. This is sort of my library of overheads that I've gathered over the last several years, but some of them are fairly recent overheads actually. But hopefully they'll be relevant. What we did at the University of Illinois is we relied on looking at images from the hologram. Very much the same as any type of photography. We projected a two-dimensional image onto a CCD camera. We looked at the particles in the image, and then we did digital processing on those images. Traditionally, that is the way to do things, is to look at the intensity of information from sharply focused images, whether it's in a hologram or from a camera. What we're doing today is we don't care what the image looks like. We don't care how good the image quality is, because we're not using the intensity information. We are actually using both the phase and the amplitude. So we're looking at the complex field coming from an object. And because of that, we can also take measurements through very aberrated windows and things. We can still get displacement information from that. And that's one of the great parts of our project here. I think I've basically said what's on this, actually. But if you want to read it for a minute, you can. It's up to you. Yeah, generally, imaging aberrations is a really big problem when you do realistic experiments, either for two-dimensional PIV or for three-dimensional PIV. Usually you have a window that's between your subject and your camera, and this window is often not flat. Very often it's a curved window. And these things, or other times you're in a tank filled with water, you're trying to image through this tank, That creates aberrations. There's lots of places for aberrations to occur, and our system can deal with these aberrations, and in many instances it actually cancels out the aberrations. Other times, if there's some residual aberrations, it doesn't really matter. We can still take measurements with our system. Okay, I think I've explained that enough. So what are the advantages with our system? I haven't explained what the system is yet. I'm just telling you why we're doing it, I guess. One is that we can take three-dimensional measurements directly from a single viewpoint, in essence, with aberrations. That's very important. Actually, our system, I've been saying holographic PIV because most of you are interested in fluid mechanics here, I believe. But this system actually works also with surfaces. So we can take three-dimensional measurements on surfaces as well. We're using a three-dimensional optical correlation of both the amplitude and phase information, not just the intensity. That's really important. Because of this, all these things, we can also use a very simplified recording geometry. So that gives us a very high signal-to-noise ratio in our system. And so our system could be very robust, much more so than traditional imaging systems. Skip that one. So, first of all, I'm going to just lay out a couple of diagrams of the optical system that I developed at the University of Illinois. And please don't worry too much about all the lenses and mirrors. I just want to give you a rough idea of how I started with this. This is the system I developed there, and I'm not going to spend very much time explaining it. Basically, this is the table of our experiment at the University of Illinois, and this is the camera that we used. I just want to do this to give you some contrast with what we're doing today. This camera right here is the most important part of the system. The rest of the optics are used for setting up the light that goes into the camera. On the back here is a hologram, and on the front is our test volume that we want to measure. Okay. Here's kind of a close-up of the camera, printed with nice, pretty graphics. This is a stereo camera at the University of Illinois. It has two viewing directions that take the light from our volume, which is here, and focuses it near the hologram that's located here. Okay. In order to look at the hologram later, we reconstruct the image back into its original volume by back projecting through the hologram. Essentially, we're using the phase conjugate reference beam. Now, I don't know what your familiarity is with holograms, so I have to be a little bit careful. But generally, when you make a hologram, you're always interfering the object beam with the reference beam. And you use the reference beam to replay the object beam later on after you've made the hologram. I don't want to get into that too much. I don't think it helps our discussion very much, or my presentation. But later, I switched to using mirrors instead of prisms for the stereo viewing. And this allowed me to get a wider, okay, I'm just really going through this fast, but this gives us two views of our subject that are 90 degrees to each other, and for various reasons that seemed like a better idea at the time. And that was my second system I developed at the University of Illinois. So this talk could be entitled The History of Don Barnhart Making Holograms for the Last 7 Years, perhaps. But I think it's relevant to talk somewhat about the history. So the system originally used two reference beams like this, and we would, one reference beam was used to record particles at one instant in time, and then we fired the second reference beam to record particles at a second instant in time. And the delta t between the two exposures determines the velocity, and you measure the displacement, how far the particles have moved between the two exposures, and then divide that by delta t, and that gives you the velocity. So we have this camera that we built, and we would back project the images back through the camera onto a CCD camera here, And we would look at that with digital signal image processing. We would do digital cross-correlation between the two images. And from this, also by looking at it from two different viewpoints, we're able to get the three-dimensional component of everything. And if this sounds complicated, that's because it is a little bit complicated, and that's part of why I'm explaining this, because our present system is much simpler. But we were able to get some very nice results from our system at the University of Illinois. Here is a jet experiment, and this is one slice of a volume. And you can see the jet nozzle here, and there's sort of a entrainment and some off vortices here. I'm not really a fluid mechanics person, so forgive me if I don't know all the right terms to use. But I believe this is, if I remember right, on the order of 40,000 vectors in this one image here, something like that. Anyway, we were able to analyze over 4 million vectors from this one hologram, 4 million points simultaneously. So that's the kind of points we can get in one instant in time. Unfortunately, our computer wasn't big enough to display 4 million points, so we could only look at a small part of that at a time. At the time, our computer could only handle about 400,000 vectors at any given moment. But anyway, here's the sidearm of the jet experiment. You can see the wake, whatever you call it, coming off here. We used cross correlation without, and as a result, this is not subtracting the average velocity. And as you can see, there's a complete flow reversal going around like that. Looks quite nice. And finally, here's a three-dimensional. This is the same area that was taken here with 2 dimensions, but this is a three-dimensional reconstruction of the velocity field. Uh-oh, I've only got 10 minutes left. I better go faster. Okay, so I haven't even gotten to the part where I'm actually talking about here, so I better be careful. Anyway, so finally, okay, so that was like our big result, and we put that into applied optics and got a nice paper out of it. Okay, so let's talk about here a little bit, okay? Not really bad, but okay. So what we're doing essentially is we make a hologram of our flow, and instead of having complicated stereo camera arrangements and all that, we just have our hologram here and our flow field right next to it, and then we reconstruct the hologram with a phase conjugate reference beam. And this time, if we put a pinhole in the flow field, or where the particles, the real images of the particles are, we can then look at a very small region in space by just limiting the size of the pinhole. When we do that, actually the whole system looks like this. We have our hologram in a pinhole, and then for those of you familiar, this gives you effectively Young's fringes in the far field from the pinhole. And now those fringes are then projected onto a CCD camera, which then go to an optical processor that many of you saw today in the lab. And then we can traverse the pinhole around to different points in space and analyze different points at wherever the pinhole happens to be. I think that's a lot simpler than the one that I showed at the University of Illinois. I'm going to move on to some results here. First of all, here are some results from one of our holograms. These are showing particle images, and some of you might recognize that these images are not very well formed. They have a little bit of distortion in them. And this is the remarkable thing about our system, is that even though it does have distortion like that, when you look at the fringes are actually very reasonable, although they, in a relative way, they're quite reasonable. And this is the Young fringes that I was mentioning in our system. Our optical processor then takes this as its input and performs a Fourier transform optically, and we get a correlation of these fringes. And the correlation is shown right here, the correlation peak. And for an in-plane displacement, you get nice parallel fringes like this. But what if your displacement is out of plane? So in other words, it's along the z direction. Then you get bullseye fringes like this. And these bullseye fringes then form in a different plane, in a different correlation plane from the end plane. Here's the correlation peak from of the third dimension. You can see the zero order is out of focus here. It's no longer tightly focused. And so actually what we have is a three-dimensional correlation that comes out of our optical processor. By measuring the distance of our correlation spot in 3 dimensions from the DC, that gives us our displacement. Here we did some tests just to check its linearity and things. I did some calibrated displacements with different known positions of our x displacement, and then looked at the correlation function, and sure enough, it's pretty linear. That's for the in-plane. The out-of-plane motion is, here's another experiment with out-of-plane displacements, and once again, it has some error, but it's fairly linear. And this is my only result so far, but this is a cantilever measurement. It's a surface rather than being a volume. But here's the out-of-plane displacement for a cantilever, and that's the theoretical shape of the cantilever. So, in conclusion, what am I going to say in conclusion? Well, I hope I demonstrated that we have something very interesting here that I believe could be the way forward for holographic PIV. It's very robust and has the potential for giving you complete three-dimensional displacement measurement from a single viewing point, and rather than having to mess around with multiple viewpoints and things. It's applicable for both fluid and solid mechanics, and it uses a correlation of both amplitude and phase within the hologram, which gives you more information and therefore makes it more robust. Finally, you can use simplified recording geometries, and that gives you better signal to noise. I think that's it. Thanks a lot. But you didn't ask any questions. You were supposed to ask me questions.
Come now.
Okay.
Anybody would like to start the ball? John?
With your optical system, over what distance can you make measurements? You have to very close in to have a small volume of viewing, or can you throw that volume a long way away from the front end optic?
Well,
because you had a fibre, I think you were using a fibre in that tank.
Right.
It seemed to me to be intruding on the flow.
well, the fiber was in the flow. That fiber locates the position of the flow. That fiber is not in the playback. It's not in the recording. In the tank, you don't have that fiber. Okay, that fiber is only used to analyze.
I see.
Yeah, it's only for analysis.
Calibrating the image or something, is it?
No, it just, that's how we analyze it. Instead of using a pinhole,
Yeah.
as I've discussed, we use a fiber.
I see.
But the distance, basically our dimensions are 50 millimeters cubed right now. We're concentrating on relatively small volumes, 50 millimeters on a side. And our distances are nominally about 100 millimeters away from the hologram. You need to have it fairly close up in order to get a wide aspect ratio so that you can get good Z resolution. In other words, your accuracy in the Z direction is limited by your how many angles get collected by the hologram. And so you need to keep it fairly close. But in our case, it's about 100 millimeters is about the distance.
Does that mean the accuracy varies over you have a cone of view that you're looking into it, so does the accuracy vary across the cone? Or is it?
There is some change in accuracy with whatever point you choose, but it's still very very respectable over pretty much any point that within our 50 millimeter volume. Okay.
Any questions?
Yes?
Is there any application to measure the surface displacement for compound surface, which is popularly used in refractive fashion? similar with the dolphin skin? Because I know it's very difficult to measure.
To measure
Surface displacement.
measure surface displacements.
Yeah, it's a compliant surface.
Compliant.
Yeah, it's like dolphin skins.
Oh,
Yeah.
right. Well, you could certainly use it for measuring surfaces like this. Of course, we are at the very beginning stages of showing this working practically, but really it should be very applicable for measuring any kind of surface.
Because I'm talking about maybe amplitude is only less than 100 micrometer.
Oh, that's actually, I forgot to mention, that is a point. Our system is most advantageous for measuring less than 100 microns of displacement. Our displacement values are usually between one wavelength up to 50 microns or so. That's usually what our 1 to 50 microns is usually the kinds of displacements we like to measure.
So you can monitor as many as 4 million points or so.
Yeah, that's arbitrary too. However many, it depends on your optics and everything and the size of your hologram. But at one time I did measure 4 billion points.
That sounds very good because that traditionally is very difficult to measure this kind of surface.
But not on a surface, that'd be 4 million points in a volume, right? Because that would be an awful lot of points on a surface. Yeah. Sure, yeah. I would be interested in any kind of applications if you want to talk to us more about an application like this, if it's an interest of yours. Yeah, sure.
Do we have any more questions? We have time for one more.
What do you do with 4 million points of data?
Well, actually, not a whole lot. That's what this allows you to do. Actually, is you've got the information there, but you don't have to get all that off the hologram if you don't want. You can pick a surface. You can pick a shape. If you want, you could just look at the contours of a flow or something. Just look at the surface. In fact. One interesting thing is you could do some of you could pick the points you want to measure as you're doing it. So let's say you want to look at equal equal velocity surfaces or something like that. You could actually determine that experimentally as you're moving your probe around, and then figure out what's the surfaces look like for equal velocity in a particular area or something. It works very well just with surfaces and not with volumes. I mean, you could just pick a surface and look at the three-dimensional displacements on that surface within a volume. They don't have to be planar surfaces. They can be any kind of shape. The information's there, and you don't have to use it all.
Okay. Thanks very much.
Thank you.
Our next speaker is...
Sorry, Chris. Okay. This is showing the correlation function as it's out of focus. And now Victor is going to turn it on and activate it and get it to focus. Okay, Victor, go ahead. Oh, there it is. It's focused. Except this camera won't focus onto the focus. Try to get it focused here. Okay, I think that's... Well, let me try it here. Oh, there. That seems to be focusing pretty good. So you can see the correlation is very nice from this. Very nice. And here's our fringes that we're actually getting. What the fringes look like. They're quite nice also. And you can just see here's the system. Okay, I'm going to turn on the light and then we'll just... Okay, this is... here's the system with the lights on. Everything's mounted, and the hologram and the camera, they're all here. And here's this thing. This is the correlation function, and here's the fringes coming into the correlation function. Now we've got to get some Z. We've got to do an experiment next to show the capabilities for Z displacement by using a rotating stage. At the moment, we're using a tank with a fixed displacement just to check that we've got the right image shifting properties that we want. Okay, just one more time on the fringes, showing you how perfect they are. These are very nice fringes, extremely nice and sharp, and our correlation peak is also very nice. Okay, yesterday I made a hologram of this tank, which was rotated so that the particles shifted in the Z direction, the out of plane direction. And before doing this, I made a computer model of the fringes and what the fringe patterns would look like, and from that I determined what the maximum displacement I could hope for to get viable fringes into the optical processor. And based on the computer model and based on some assumptions about the SLM in the optical processor, I came up that plus and minus 50 microns of particle shift would be the maximum viable displacement, which is 100 microns total. And from this, I arranged to set up this experiment. The other thing I determined was, based on the optical fiber, because the fiber has a limited coverage on the hologram, it's fairly large coverage, but it's still not complete and entire. I determined that I could get 20 millimeters of usable image space from along the parallel to the plane of the hologram, without losing uniform illumination adversely, and that's plus and minus 10 millimeters from the center of the hologram is what I determined. Okay, so taking those two figures together, I determined that at a point 10 millimeters from the center of the hologram, I wanted a 50 micron displacement in my particles. And so plus and minus 50 microns at a plus and minus 10 millimeter positions in the particles space. And that's what I accomplished. But in order to do that, I had to put a feeler gauge, what I call a feeler gauge, some people call it a dial gauge, at the end of the platform, which is actually located a distance of 40 millimeters from the pivot of this system. So 40 millimeters means that I have to have a 200 micron displacement at this 40 millimeter distance. The 40 in order to give me a 50 micron displacement at the 10 millimeter distance. And so I set this up to displace 200 microns over 40 millimeters. And very simple as I adjust the stage, I can then rotate the dial. The needle of the dial gauge follows the displacement of the stage. And this seems to work very well. And I made a hologram of this, and today we are analyzing this hologram. We are going to analyze it, and we are going to make a plot as a function of position, linear position along parallel to the hologram. We'll make a plot of the displacement at each position, and that's what we're after next. One final comment is that I decided to use a 3-second exposure for exposing this plate, and the fringes are not quite as bright as I would like for them to be, and I'm not sure if it's because of the exposure or if it's just because we had some slight vibrations during the exposure. But The fringes are there, and they're usable, and but they're less bright than the holograms I made the other day with a 2-second exposure, which leads me to think 3 seconds should be fine, but the brightness is being affected somewhere when we made this hologram. And that's all for now. Okay, today I worked on improving the lens pinhole configuration. Here is the final configuration that I've developed up till now. Notice the well, the fringes are halfway decent, but what I ended up doing was I took this lens here and I put I took out, this is a compound lens. Let me unscrew this and I'll try to attempt to show what I did. In the back of this, I placed another pinhole, which is aluminum foil adhesive tape, and I actually attached it directly to the iris of the lens, and then punched a 0.5 millimeter hole through it. And the reason I know it's 0.5 millimeter is because I used this 0.5 millimeter pencil and punched that into this aluminum foil after sticking the aluminum foil first over the iris and then just punching the middle of it with as I discussed. And then what I did was this is actually buried behind one lens element. So there's a lens element in the way on top of this, which I had to remove first. Then I put the pinhole, the iris in place, the pinhole over the iris, and then I put the lens back. And that seems to be the best solution until now. The only thing that might be a problem is I might not have the pinhole exactly square with the center of the lens, and if that is, it's very likely, in fact, it's not exactly centered, and I should probably develop a jig to hold this lens so I can exactly puncture it in the very center. What I did though was I used the iris as in its smallest size. I used it as a mask, as a way of determining the center of the lens, and then I punched it through the middle of the iris just by eyeballing it. Okay, but that seems to give a pretty good, well, the best fringes that I've been able to get so far. What I was hoping for originally was to use this, which is also a pinhole that has been punctured into this aluminum foil with the 0.5 millimeter pencil, and then I used this iris here as a label, or as a guide to get to the center, to find the center, and I laid this iris over it first, and then puncturing the aluminum foil with the pencil, and that worked pretty well. These are a series of stacked threads, C-mount threads, to get some distance, get some distancing away from the pinhole. However, when I place that in the position of the camera, the fringes are no longer uniform. In fact, they're very different from being uniform. I will stop the camera and put this pinhole in place just to show you what the fringes look like, because they're very disturbingly uneven. Okay, so here I've got this pinhole mounted on the front, and the fringes are displayed here, but it may be difficult to see the unevenness here, but when I try to look at the correlation functions, they have a great deal of distortion in them, and they're not very convincing. As far as I can tell, this using a pinhole directly is not going to work, because actually there's a curvature this way up here, and then down here there's a curvature that's this way, and in the middle the curvature is somewhat linear, but it kind of goes like this and then goes like this over here, and then somewhat linear here. So there is something wrong with using a pinhole directly without a lens, and it's very upsetting to me because I would love to use it. I feel that it would have the least amount of, well, it seems to be geometrically the most accurate. However, it isn't. In fact, the angle to spatial mapping is not right. It's wrong. And we're not able to get good correlation functions with it, even though we have good contrast fringes. The fringes are very nice contrast, nicely contrasted, but they are just not accurate. They're not curved right. The curvature is not uniform, and they're not even consistent to giving a spherical wavefront. There's something other than spherical, maybe hyperbolic perhaps. I don't know. Anyway, that's the story. So we'll switch back to using a lens instead. Okay, I've got the lens back in place. Now what we have here are some very straight, consistently parallel fringes, which are correspond to the center of our measurement hologram, which has parallel displacements in the image space, and the correlation looks quite good, although right now it's out of focus because the computer shut off and I don't know how to focus it. But that's what we have. So, solution: 0.5 millimeter pinhole with a lens, with a camera lens. I did experiment with using some single lens elements instead of a camera lens, but I had very much difficulty finding a lens element with the appropriate focal length on it. I had tried several. I tried a 40 millimeter focal length, which I thought would have been the best possibility, but unfortunately this lens gave too much magnification, and I wasn't able to see all of the hologram. So another thing I could try doing in the future is getting a different lens that has the appropriate magnification to give us a full view of the hologram, but I would have to do some more calculations to determine that. I thought I determined 40 millimeters, but here in fact is where I did my calculation. I determined that I wanted about 42 over 1.2, about 40 millimeter length, but I think I was off on that, and I have to redo that one to figure it out, what we need. Okay, so that's it. I'm signing out for the day and continuing tomorrow. We need to make some more holograms now. I'll probably stop with messing around with the lens for a while because we have a lens here that does a pretty good job. By the way, the depth of focus of this thing is, with a smaller pinhole in place, is much better. It used to be up around 2 millimeters, and now it's under a millimeter depth of focus, total depth of focus. About plus 0.5 to minus 0.5 millimeters, roughly, depth of focus on our images, which is very exciting to me because that's my threshold for what I think is a workable PIV system, is to give a millimeter resolution, at least in the depth direction. So there you have it. I'm signing off now. Okay, today I made 3 holograms. Each hologram was slightly, well, I did a different arrangement. For each hologram, first of all, I made my displacement 1/4 the value of what it was before. So this is about 25 microns at, well, so that brings it down to about 12 microns at 10 millimeter distance, and 12.5 microns, I believe. The other thing is, the first hologram I made hologram number 1, I used a straight reference beam without any expansion. The second hologram, I used a light sheet using this cylindrical lens as a light sheeting device. And then the third hologram is the one I'm showing here. I put in a negative lens, and now I have an actual volume, a little beam of light shooting through the hologram volume. Just to show you what the second, I'll put in the second light sheet just to show this effect. So I'm taking out, so this is the first hologram, just a single beam of light. And then the light sheet is like this, where it spreads through the space rather distinctively, like such. Okay. Each hologram was made with roughly a 3-second exposure, somewhere between 3 and 4 seconds. I just count it out loud verbally, so there is a substantial amount of variation in the exposure times, but it's between 2 and 5 seconds of exposure for each one. This dial gauge is actually 40 millimeters from the pivot point, and I use a 25. This is showing here a 25 micron displacement. No, 50 micron displacement, and that should therefore correspond to but the actual distance I'm interested in is only 10 millimeters from the displacement, so 1/4 of 50 microns, which is 12.5 micron displacement. Okay, next I'm going to view some of these holograms in the playback rig to see how well they perform. Okay, I developed the 3 holograms and made them, and now I've viewed them. However, the particle brightness is somewhat limited in these holograms. This is the one for the single line, that is without any, not planar, but just single line, I believe. And even then, the brightness is somewhat sketchy, but it's enough. This is bright enough to give us fringes, and the fringe spacing seems to be pretty reasonable. However, we seem to have a pretty good balance on the fringe spacing with this new, with the new offset, or the new displacements that I chose. Seems to work pretty well for the fringes, because we start here fairly large fringes, then up here they get fairly fine, and I think that's a nice range there. I can't show you the correlation function because this computer's not running right now. The challenge ahead of me, though, is to make the particle images brighter, and to, well, that's it, to get brighter particle images so we can work with the volume holograms. I did view the volume hologram with earlier, and it's too weak to give you really any good fringes at all, but the particle images themselves were visible, just barely visible on the screen here, the particle images when they're focused into the camera. But the actual fringes are not there, because they're just too weak for giving us good fringes in the volume. I think it's my exposure time needs to be adjusted. Also, I need to baffle off the scattered light around the tank so that only the light scattering from our the area of interest gets to the hologram. I think that will help our noise signal to noise. Finally, should attenuate the reference beam slightly and use a longer exposure time and get more. That way, I get more of the energy coming from the objects themselves. Get brighter object to beam ratio to reference beam ratio. Okay, this is the end of the tape, and on the next tape we will discuss well, what happens next. But I think this is all I will do for the most part today.